Hello everyone, welcome to another video on quantum field theory. This video is a continuation of my last video on quantum field theory, where we actually solved for the direct solutions to the Dirac equation. These solutions were done in the rest frame, and now we will be expanding upon those solutions. So here is our game plan for this video. First, we will talk more about our notation, then talk about the spinor field time of evolution, then talk about the Dirac basis, then the Lorentz boost, and then finally get the actual general solution. Because remember, in our last video, we only got the rest frame direct solutions, but we haven't yet taken a superposition of those solutions, and we haven't actually boosted them to the general frame. And we will be doing two of those things in this video. So let's begin. Okay, so first of all, we all hate it, but we have to do it notation. So, in my last video, I used this notation for the while spinners. Here's my Dirac bispinor, and here are my two while spinners. Now, when I talked about the ansatz for the Dirac equation, the motivated ansatz, I used this. This is a abuse of notation. It doesn't really matter that much, right? Like, there's nothing objectively wrong with this. We just have to keep in mind that we're kind of changing the meaning of these while spinners. So, our solution was correct. It's just that we could have used a better notation. So, remember, this is these are the components of the Dirac bispinor, right? So, really, we wouldn't be adding any extra term to it, since this is just the general form of the Dirac bispinor. So what we really should have done was instead to use different variables, say alpha and beta, and then tacked on that e to the minus imt term there, and that would be equal to these while spinners, where chi would be 1, 0, e to the minus imt, or chi could be 0, 1, e to the minus imt. And then remember that we found that chi equals epsilon, and then we found that chi equals epsilon for particles, and then chi equals minus epsilon for antiparticles. So that's what we really should have done. But again, just notation, it's the same concepts, it's the same physics, so don't worry too much about that. Just clearing it up. And we are going to introduce a bit of new notation in this video to make things a bit more easier for us. So yeah, this is the bad notation. This is the cool notation, and we're gonna add some extra notations in this video. Now, remember that before we derived 4 direct solutions. We derived psi 1 was 1, 0, 1, 0, e to the minus imt. Psi 2 was 0, 1, 0, 1, e to the minus imt. Psi 3, that does not look like a psi, was 1, 0, minus 1, 0, e to the imt, because antimatter, right? Then psi 4 is 0, minus 1, 0, minus 1. No, it's 0, 1, 0, minus 1, e to the imt. Now, this can be a bit of a hassle to write all down, so what we can instead do is use a bit of a simpler notation. So instead, let's actually have psi to the I, and we're going to let that be ui for the matter, and then you have psi tilde I equals minus vi for our antimatter terms, where u1 will be defined as 1, 0, e to the minus imt, and e2 is defined. Also, this is all again in the rest frame, so u2 is going to be 0, 1, e to the minus imt. v1 will be defined as 1, 0, e to the imt. Then v2 will be defined as 0, 1, e to the IMT. Okay, so why are we doing this? Because, okay, so let's break all this down. So here, what we've done here is we just wrote all of this in a more compact form. So 4 components, and we wrote it as 2 components, right? So again, these would be our while spinors, but all we've done here was we've indexed them. So for psi1 here, right, instead we just have psi to the I. And so psi1 would just be U1, U1, and U1 is 1, 0, e minus IMT, right? Well, yeah. So U1 is 1, 0, e to the minus IMT, and that's how we get 1, 0, 1, 0, e to the minus IMT. For I equals 2, you'd have U2, U2, and that's this, and we'd get this. So we're just writing this in a more compact form. It's kind of like Einstein notation, but not exactly Einstein notation. We're just taking those 4 solutions, writing them in 2 for matter and antimatter, and then defining these index relations. So I hope that makes sense. Just a more compact form here. And it is this form that we are going to use when we take the linear combinations of the Dirac spinors. But before we get to that, let's actually talk more about what these solutions actually mean. So remember that in the last video we actually solved for the solutions, but we didn't talk about what they meant. Well, we talked about what the spinors part of it means in the in my video about while spinors, which I recommend watching, but we didn't talk about how the spinor field evolves over time, and that is our next part of this video. So let's actually do that. Okay, so how does the spinor evolve over time? Okay, so let's take some spinor. Let the spinor be 1, 0, 0, 0. So what does the spinor mean? 1, 0, 0, 0. This spinor just describes a left chiral field that is spin up. If you guys didn't know that, watch my video about while spinors. I talk all about that. But this describes a field that is left chiral and spin up. Now notice that this isn't actually a direct solution to the Dirac equation, because if you guys can recall, these were our solutions, and there is no 1, 0, 0, 0 here, right? So this isn't a direct solution. However, remember with any linear equation, the Dirac equation is a linear equation, we can actually take linear combinations of those direct solutions to get new solutions. Now we have to make sure that our linear combination is normalized, since the Born rule requires that our fields be normalized. So we can actually, this can solve the Dirac equation, but to show that explicitly, well, I should probably change my terminology here. This does solve the Dirac equation as long as it can be written as the linear combination of those Dirac solutions. And it actually can. I'll show you what that looks like. So 1, 0, 0, 0. You can write that as 1/2 times 1, 0, 1, 0 minus 1, 0, 1, 0. Check it yourself that this actually equals this. And remember that this is actually just psi 1, and this is psi tilde 1 of 0, right? Because remember that our solutions actually depend on time, right? So this is psi 1, 0, psi 1 tilde 0. So this, of course, implies that this spinor field is at t equals 0. So this does solve the Dirac equation as it can be written in terms of the Dirac spinor solutions. And this is a field configuration at t equals 0. So what this means is that our field starts out in this purely spin up left chiral field, okay? And that can be written as a superposition of initial psi 1 and psi tilde 1 states. Okay, I want to make sure that makes sense. That made no sense, but okay. So how can we find how this spinor field, this 1, 0, 0, 0 spinor field will evolve over time. Because remember, this is the initial state at t equals 0. How can we find out what it looks like at t equals, well, 10 or t equals pi? What can we do? Well, if you guys remember from like normal elementary quantum mechanics, what we do is, of course, we rewrite it out as a superposition of these stationary states. We already did that. In this case, these would be, spinor states, Dirac solutions of the Dirac equation. So we already did that. And then what we do is we attach time dependence to each of those solutions to finally get the time dependence of this. So in other words, we attach we put time dependence on this and this to get the time dependence for this. That's all we do. So what we do now is we would just attach this e to the minus imt term here, minus e to the imt. So we just put time dependence on these in order to get psi of t. And that's our answer. That is our answer. So let's actually evaluate what this field is at different moments in time. So, of course, at t equals 0, we get 1, 0, 0, 0, the initial field configuration. But what about t equals pi over 2m? So t equals pi over 2m. What does our field look like at that moment in time? Well, let's find out. So we'd have psi of pi over 2m equals 1/2 times 1, 0, 1, 0 e to the minus I m pi over 2m minus 1, 0, 1, 0 e to the I m times pi over 2m. You can probably see why I chose pi over 2m as the time, because conveniently these m's will cancel out. So what we really have here now is that psi of pi over 2m is going to be 1/2 times 1, 0, 1, 0 e to minus I pi over 2 minus 1, 0, 1, 0 e to the I pi over 2. So our field is a linear conversion of our matter spinor field and the antimatter spinor field part. Okay. So what to do now? Well, we just have to evaluate what this is by using the Euler's formula. So remember that E, let's move this down a bit. Okay, so E to the I pi over 2 is just cosine of pi over 2 plus I sine of pi over 2, right? So what is cosine of pi over 2? Well, cosine of 0 is going to be 1, right? And cosine of pi is going to be minus 1, and the cosine of 2 pi is 1, and so on. This implies that cosine of pi over 2 is going to be 0. Okay? What about sine of pi over 2? Well, sine of pi is going to be 0. Sine of 2 pi is going to be 0, implying that sine of pi over 2 is going to be 1. So e to the I pi over 2 is going to be 1. Okay? What about e to the minus I pi over 2? That's going to be cosine of minus pi over 2 plus I sine of minus pi over 2. Remember that we can exploit the even and oddness of our, this is sine of pi over 2 is 1, right? So we are left with I, actually. Because cosine of pi over 2 is 0, sine of pi over 2 is 1, so you have 1 times I. 0 plus 1 times I is just 0 plus I. So this should actually be I. My bad. So e to minus I pi over 2 equals cosine of pi over 2. Cosine of minus pi over 2 plus I sine of minus pi over 2. Cosine is an even function. This is going to be cosine of pi over 2. And then this will be plus minus I sine of pi over 2. Since sine is an odd function, so cosine of pi over 2 minus I sine of pi over 2. And the cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get minus 1. So here's I. Here's going to be minus 1. All right. Okay, so now we just rewrite this. Psi of pi over 2m. What was that again? Psi of pi over 2m was going to be 1/2 times 1, 0, 1, 0 e to minus I pi over 2 minus 1, 0, 1, 0 e to the I pi over 2. Now we just found out that e to the I pi over 2 is minus 1. And that this, sorry, it's minus I, and this is I. Therefore, psi of pi over 2m is going to be 1/2 times 1, 0, 1, 0 times minus I minus 1, 0, 1, 0 times I. But what we can do now is we can factor out that minus 1 term. So this is going to be equal. Let me just move this paper up a little bit. This is going to be equal to minus I over 2 times 1, 0, 1, 0. This is already factored out. This is going to be a plus now. Plus minus 1, 0, 1, 0. Okay? So minus I over 2. Okay, so what's 1 minus 1? That's 0. 0 plus 0 is 0. 1 plus 1 is 2. And now we just distribute this 1/2 term inside of here. Get minus 1 times 1/2 times 0, 1/2 times 0, 1/2 times 2 is going to be 1. So you have 0, 0, 1, 0. And notice that this is actually the right chiral field that's spin up. So you get minus 1 times the right chiral field that was spin up. This is actually very interesting. You guys might not see how it's interesting right now, but I'll show you why. Because remember, he found that psi, initially psi naught, well, psi of t equals 0, was purely left chiral that was spin up. And just from that psi of, what was our time, pi over 2, pi over 2m, is minus the spin up right chiral field. So this is t equals 0. Here's t equals pi over 2m. It's not actually the spin up right chiral field. It's almost the spin up right chiral field. We just have a negative 1 term there. So it's almost, well, it's the opposite, because you could say, of the spin up right chiral field. So what happened was that our field oscillated from a purely left chiral spin up field, and it turned into a purely right chiral spin up field with a negative 1 component there. So what we've shown here was that when you let the Dirac bispinors evolve in time, our field is going to oscillate between left chiral and right chiral. So if we could put this in words, so here's our physical interpretation. So remember that we are working in the rest frame, right? We're working in the rest frame for k equals 0. So we had one spinner at the origin. We had one spinner at the origin, which was 0, 0, 0, 0. It's because we have t equals 0. Okay. What happened? So, well, not what happened. So we have a spinner at the origin, and everywhere else, well, is 0. So we only have one spinner at the origin. Okay. Because we had 1, 0, 0, 0, right? E to the minus I m t, and t was 0, right? There's no like spatial terms here. T was 0, so this is just 1. So we just have one spinner at that origin, and everywhere else, there is no spinner. This corresponds to us like attaching our coordinate system at that spinner. That spinner isn't going to be moving in its own frame, and it's going to be that everything else is moving relative to that spinner. And that spinner observes itself with momentum k equals 0. Okay, that's just relativity. And the spinor goes from a left chiral field, and then it mixes with left chiral and right chiral components. So you guys can do this yourself. You can tweak the value for t. So like if we had t equals 0 and t equals pi over 2m, if we had, say, t equals pi over 2, just tweak your value of t, you're going to find that our spinor field is going to have left chiral and right chiral components. So it goes from initially left chiral, and then it mixes between the left chiral and left chiral and the right chiral components, and then it becomes a right chiral field with that -1 component there. And then this is going to repeat the process all over again. So it oscillates between left chiral to right chiral, and then in between it mixes between left chiral and right chiral. And this is like really, really interesting here, because we just have, well, kind of like one field like at the origin, and it's changing as time goes on. So, and in fact, if you change the value for m, this field will oscillate faster or slower, because if we let m be like really large, then that means the time it takes for it to go to the left chiral state to the right chiral state is going to be smaller. But if m is really small, it'll take more time to oscillate between the left chiral and the right chiral field. Okay, and yeah, it just oscillates between them. We call those chiral oscillations in QFT. Now, there's actually a very more fundamental reason as to why the mass affects like the amount of time that it oscillates, and it's because the mass. Well, we haven't covered this yet. We will cover this in the future. But the mass, like in quantum field theory, is related. Like the mass term in the Dirac equation is related between interactions between the spinor field and the scalar field, or we say that the mass is coupled with the scalar field. So we have the spinor field, and the mass tells us like the coupling between the spinor field and the scalar field. And when the spinor field and the scalar field interact, well, then our chiral state of our field will change. In this case, it change from the left chiral state to the right chiral state. So when our spinor field interacts with our scalar field, it will actually change the direction or the state of our field, if that makes sense. And the math will tell us how much it will change, because the mass tells us the coupling strength between the spinor field and the scalar field. Now, that's actually new material. I'm just giving you guys a sneak peek of what's next, I guess you could say. So yeah, that's the physical picture of our field evolving over time. And you could, of course, like put any value of t that you want and just see what you get. That's your homework for today. Okay, so what's next on our list? Okay, let me just get, where is the list? Can't find it. I believe what we have to do now is talk about the Dirac basis. Yeah, here it is. Next is the Dirac basis. Okay, so in the Dirac Lagrangian, we actually see this term. So, where this is the Dirac bispinor, and this is said to be the Dirac adjoint. Okay, and the Dirac adjoint is defined as the complex conjugate of the Dirac spinor times the zeroth gamma matrix, or times the zeroth gamma matrix. And this is just a term that appears in the Dirac Lagrangian. You guys can see look up the Dirac Lagrangian yourself and derive the Dirac equation from that. in my space and algebra video, we derived it with a different approach by factoring out the Klein-Gordon equation, but you could also derive it from the Dirac-Lagrangian, and this term appears there. So that's where it comes from. So we can actually apply a change of basis to this whole thing. So what do I mean by change of basis? Well, what we can actually do here, so let me just rewrite this again. Okay, so what we can do here is we can actually multiply this thing by this matrix, by this n matrix and its inverse. So what we are really doing here is multiplying this by the identity matrix, right? And multiplying something by the identity matrix shouldn't actually change that thing. You shouldn't like fundamentally make it a different object. So what we're doing here is we are multiplying this whole thing by the identity matrix and splitting that up into some matrix n with its inverse n to the -1. Okay, that's all we are doing here. And now we can actually wait, what do we actually do now? Okay, actually we could actually add another matrix right over here. So we are going to add another matrix over here. Okay, so what we've done here is we just multiplied by 1 twice. So you have n to minus 1 here, and then n minus 1 n. So we should have the same exact equation, but you're gonna see that it's going to look a bit different, since we can actually pair this Dirac adjoint with this n over here. Or sorry, we can pair this Dirac adjoint with this n minus 1 to get the Dirac adjoint prime, where the Dirac adjoint prime is defined as n minus 1 times the Dirac adjoint. And then we have this n given mu, n minus 1. We can call that gamma mu prime. So gamma mu prime is going to be defined as n gamma mu n minus 1. And this n times the Dirac spinor, you can call that psi prime, where psi prime is defined as n times the Dirac spinor. So what we've done is what we call a change of basis. We've pretty much multiplied by 1, and by doing so, we kind of get we make the components of our gamma matrices and our Dirac spinor look different in the process. So I hope you guys can see like what we're doing here. We're just like pairing this together to get this together to get that, and then that's together to get that. Okay. And depending on our matrix n, we are going to find different components for our Dirac spinor. It's kind of like how if I have, say, 10 divided by 4, right? I can multiply 10 divided by 4 by 1 over 2 divided by 1 over 2. So I'm multiplying by 1, right? But I'm splitting 1 up into 1 over 2 divided by 1 over 2. And that gives us 5 over 2. So it looks different when we multiply by 1 over 2 over 1 over 2. Now 10 over 4 and 5 over 2 are still the same exact values, right? But just looks different when we change our basis, right? That's like pretty much what we're doing here. We're just multiplying by 1, right? And we can split 1 in a certain way as to where the components of this look different, but they're still evaluated to be the exact same expression, all right? And the matrix that we actually care about, the one that we are actually interested, is using the matrix, let me see if I can find it, 1/2 times 1, 1, 1, minus 1. So why are we using this matrix? Well, we can in principle use any matrix that we want, as long as it has an inverse that you would like multiply by it to get the identity matrix. And this actually does the job. You can check it out yourself. And the reason why we use this matrix is you'll see that it simplifies our components to the Dirac, bispinor. And again, we'd multiply this matrix by our spinor to get our new spinor components, right? So we'd multiply this by a spinor to get our new spinor components. And our old spinor, we say that it's in the chiral basis. Throughout this whole series, we've been using what is called the chiral basis. But now, when we multiply that by this matrix, it's going to make our components look different. And we call the Dirac spinor in the new basis, we call that the Dirac basis. The chiral basis is sometimes called the Weil basis. This is sometimes called the mass basis. And our Dirac components, you could actually carry the computation yourself, but the Dirac, what was I going to say? The Dirac bispinor represented in the Dirac basis look like this. So we have psi 1 becomes u1 e to the minus I k mu x mu. Psi 2 equals u2 e to the minus I k mu x mu. Psi 3 equals v1 e to the I k mu x mu. And then psi 4 v2 e to the I k mu x mu. Where u1, before u1 looked like 1, 0, 1, 0, but now u1 is going to look different. Now, let me actually check my notes. What's u1 look like again? Okay, so yeah. So u1 is going to look a certain way, and here's what it looks like. I'm too lazy to actually write this entire thing down because you guys can see it's very long. So now if you wonder why are we doing this, it makes our components look, well, look really complex. Well, it actually makes it simpler. What we've actually done here is that we've boosted these components. So previously we had u1 is like 1, 0, 1, 0, right? Sorry, we had that u1 is like, wait, what is u1 again? Yeah, u1 is 1, 0, 1, 0, but that was in our rest frame. But if we were to boost that spinor, our components would look a bit not nice to work with. So what we've done here is that, again, we had these components, and we had the rest components, and we boosted them to a general frame, and that general frame looks like this, or this is some normalization constant. So if you were to actually write down let me just, I know I'm kind of being not clear now, so I want to make it more clear about what I'm saying. So, so we have the Dirac spinor, right? The Dirac spinor is like 1, 0, 1, 0 e to the minus IMT. It's 0, 1, 0, 1 e to minus IMT. It can be 1, 0, minus 1, 0 e to the IMT. Then it can also be 0, minus, not 0, 1, 0, 1, then 0, minus 1 e to the IMT, right? If you multiply each of these by that n matrix, our components will, of course, look different. And then after doing that, we boosted it by applying the Lorentz boost to a general frame, because these are in the rest frame. So we apply this n, and then we boost it to the general frame. Our components now look like this. That's what I'm saying. So remember before we could have written this as psi of ui, and then we could have written this as like these parts, and then we could have written the antimatter parts as like, I believe it was vi minus vi, right? So if you do that, and then you position the most general frame, you get these components, okay? These are the components that you get. So that's where they come from. Now, if you guys want to see like the actual computation of boosting to the general frame, it's a bit tedious, but you guys can see, I believe Peskin and Schroeder will carry out this computation. So you can see that as a reference for the computation. And then, of course, So this is all in the what we call the Dirac basis, by the way, because we changed our basis. If we still work in the chiral basis and boosted our spinor to the general frame, our components would look different, and they would be hardest to work with. You can try that yourself and see. Also, here I got a bit lazy to write it down. It's just going to be this for here, this here, and 0, 1. Just to write it down again. Okay, so what else? Also, yeah, what's nice about the chiral basis is that our components are related to the spin state. But now after changing it to the Dirac basis, like this 1, 0, 1, 0, sorry, 1, 0, 0, 0 would no longer represent the purely spin up left chiral field. That interpretation only makes sense in the chiral basis. So that's the benefit of the chiral basis. Personally, I prefer the chiral basis for when we want to get physical meaning out of our Dirac spinners. But if we care about computing something, the Dirac basis is usually the way to go. Though we could do it in any basis we want. We could like choose n to be anything and get like other like weird solutions. Like there's like a Majorana basis and stuff. All of those things like are pretty cool. But yeah. And then of course we can take the general solution of the Dirac equation. Because remember, with the coordinate equation, we just take a superposition, which is the linear combination of those plane waves. And we do something similar for the Dirac equation. Now you guys can't see the full thing, but it's pretty long. But here it is. So yeah, here are our plane waves. This looks complex, but I'll break it down for you. Here are our plane waves, right? And then these are just the spinor. What do I call it? These are just the spinners. Oh, sorry, not spinners. What's the name for them again? Like these are like the structure spinners, I guess you could say, right? So these are the plane wave basis, and these are well, these things, right? These are the internal structure spinners, right? And when we take a linear combination of these, right, over all of K, we pick up coefficients in front of them that depend on K. And since K is continuous, we'd integrate over all of K. In this case, we are integrating over all 3 momentum K. And we have, and in doing that, we pick up this term over here at the bottom. So, and then here we have a summation, r equals 1 to from r equals 1 to 2, because we have, well, 2 configurations for our spinners. So we'd have to sum over those configurations too. So yeah, that's, well, all for today's video. I wanted to get shorter, but, well, I guess we ran a bit over time. And so yeah, also, yeah, these are coefficients. These like would be like momentum functions. And yeah, these are just solutions of possible spin configurations in the superposition of the plane waves. And that's all for today's video. And in our next video, I'm not sure what we will do, but I think we might get into particle states in QFT. We'll see. So I hope you guys enjoyed this video, and if you guys liked it, consider sharing it. And yeah, have an amazing day. See you guys later. Bye.